In this topic we're going to be discussing the factors which affect the rates of chemical reactions, how quickly the reactants are used up or the products are formed. In our everyday experience we encounter chemical reactions that we can consider to be fast. Combustion reactions, for example in a motor car engine or a rocket motor. The ultimate fast oxidation reaction would be an explosion. We also encounter reactions which are very slow, sometimes so slow we don't notice a reaction is taking place. Rusting, fermentation of fruit sugars to form wine, or the production of bubbles of carbon dioxide that makes dough rise in baking are good examples of slow reactions. Not just in chemistry, but in all situations, a rate is defined in terms of how much of something per unit time. Speed is a rate of movement, so it's measured in terms of distance per unit time, for example miles per hour. In chemistry we're interested in amount of reactant used or amount of product produced per unit time, so our units of rate will typically be measured as something per second. There are various different experiments we can do to measure the rate of a reaction, depending on what we can observe during the reaction that's easy to measure. One example would be the apparatus here, used to measure volume of gas produced in a certain amount of time, or the time it takes for a certain volume of gas to be produced during a reaction. We could, for example, note the reading on the gas syringe every 5 seconds after the reaction starts, until the reaction finishes or the syringe is full. A similar experiment might be performed where, instead of measuring the volume of gas produced, we measure the mass lost as the gas escapes into the atmosphere. Like in the previous experiment, we could measure the time taken for the mass to decrease by a certain amount, or we could note the reading on the balance at regular time intervals as the reaction proceeds. In this experiment we're not observing the production of a gas, but of a precipitate. We place a mark underneath the flask and measure the time it takes for enough of the precipitate to be formed that we can't see the mark anymore. When we make measurements at regular time intervals of amount of product formed, we can plot a graph to show this data. If we plot time on the x-axis and the amount of product formed on the y-axis, then the gradient of the graph at any point is the amount of product divided by time, which is the rate. The steepness of the graph therefore shows us the rate of the reaction as time goes on. The gradient is steepest at the beginning, showing us that the rate of reaction is fastest at the start. As time goes on, the gradient of the graph decreases, showing us that the rate of reaction slows down. Finally, the gradient becomes zero. This corresponds to the rate of reaction becoming zero because the reaction has finished. One of the reactants has been completely used up. A similar trend would be seen in an experiment where we measure the amount of a reactant used up at regular time intervals. The curve now curves downwards as the amount of reactant decreases, but the gradient is still steepest at the start of the reaction and gets less steep as time progresses until the reaction finishes and the gradient becomes zero. To check that you've understood what these graphs of amount of reactant or product versus time are telling us, look at the 3 different experiments plotted here. How can you tell which reaction has the fastest initial rate? How can you tell which reaction finishes first, and what will be the effect of changing the reaction temperature in terms of the shape of the graph? Pause the video whilst you think this through. The fastest reaction is the one with the steepest gradient, the blue one. The reaction which finishes first is the one that becomes flat with a gradient of 0 soonest. Again, this is the blue curve. If we did the same reaction at 2 different temperatures, the only thing we'd change is the rate of the reaction, so the final amount of product made would be the same in each reaction. It would just be made in less time when the reaction was done at a higher temperature. This means that the graphs for the 2 different temperatures have to finish with the same amount of product being made, so they must be the blue and green curves. The blue curve is steeper initially and the reaction finishes sooner, so this must be the reaction at a higher temperature. To understand how the rate of a reaction is affected by factors such as temperature, we use a model of how a reaction works which we call collision theory. If we start with, for example, a mixture of methane molecules and oxygen molecules, these gas molecules will be moving around randomly with various different speeds and hence various different amounts of kinetic energy. The first idea in collision theory is that for a reaction between these molecules to happen, the reactant particles have to collide with one another. The second idea in collision theory is that not every collision results in a reaction taking place. There is an amount of energy called the activation energy for the reaction, and this is the energy needed to break the bonds in the reactants that need to be broken in order to form the products. If the reactants collide with more energy than the activation energy, then we have a successful collision and these molecules react to form the products. If the reactants collide with less than the activation energy, then the collision is unsuccessful and the reactant particles just bounce off one another and carry on moving. We can see how collision theory is telling us that the rate of a reaction is determined by the number of successful collisions per second, which we could also refer to as the frequency of successful collisions. Collision theory works with solids too. The only difference we have to remember is that a lump of solid reactant can only have collisions happening on its surface. In this example, the orange blobs represent the atoms in solid zinc, and the blue particles represent hydrochloric acid in solution. For a successful collision, a hydrochloric acid particle has to collide with the surface of a lump of zinc, and has to collide with energy greater than the activation energy for the reaction between zinc and hydrochloric acid. We can use this model to think about the different factors which might affect the rate of a chemical reaction such as this one. We've already looked at the idea that raising the reaction temperature would increase the rate of a reaction. Increasing the pressure of reacting gases, or the concentration of reacting solutions, or increasing the surface area of a solid by breaking it down to smaller chunks will all increase the rate of a reaction. In addition, we can also increase the rate of a reaction by using a catalyst. We'll now look at each of these factors in turn and use collision theory to explain how they'll affect the rate of a reaction. We're going to be using phrases like more frequent successful collisions or more particles per centimetre cubed. It's important that you learn and use phrases as precise in meaning as these, because using phrases like more collisions or more particles is going to be too imprecise. When we talk about the concentration of a solution, we're talking about how many solute particles there are per centimetre cubed of the solution. Concentrations have units of moles per cubic decimetre, or moles per dm cubed. We should know that 1 dm cubed is 1000 cubic centimetres. If we increase the concentration of a reactant, then we have more reactant particles in the same volume, so more particles per centimetre cubed. Because they're closer together, we'll also have more collisions between the reactants per second, and that means successful collisions will happen more frequently, and the rate of reaction will be faster. In fact, we can make the prediction that if we double the concentration of a reactant, then there will be twice as many reactant particles per centimetre cubed, so successful collisions will take place twice as often, and the rate of reaction will be doubled. We can easily set up an investigation to see if this prediction holds true experimentally. In this experiment, we're reacting magnesium with a dilute acid, which will cause the magnesium to dissolve, forming a magnesium salt, and bubbles of hydrogen to be produced. The hydrogen flows through the delivery tube and can be collected in an inverted, water-filled measuring cylinder. We'd need to keep the mass of magnesium, the volume of the acid, and the temperature the same, but we'd change the concentration of the acid, and for each different concentration we'd measure the time for a certain volume of gas to be produced. For example, the time for the measuring cylinder to be completely filled with hydrogen. If we're doing experiments which require us to make quantitative measurements, then we'd also need to think about reducing the effects of experimental errors. For example, we repeat each experiment so that we can take an average of the results. This improves the reliability of the results by reducing the effect of the random errors that affect each experiment. We can also see, when we repeat an experiment more than twice, whether there are any values which are not consistent with each other. We call these anomalies and do not include values of this kind in our averages. When we look at our repeats, we can see how close together the repeated measurements are. The closer they are, the more reliable. Here are the results from an experiment where the concentration of acid was varied from 0.4 to 2.4 moles per dm cubed. Each experiment was repeated 3 times. The first thing we should notice is that for each different concentration the repeat values are quite close together, except for the first experiment with concentration 0.8 moles per dm cubed. This is clearly a long way from the value we obtained in the second and third repeats, and is an anomalous result, so we put a ring around it and don't include it in the average. Notice also that this was the first experiment at 0.8 moles per dm cubed concentration. If we hadn't done repeats, we'd never have known that this value was an anomaly. We can display the results in the usual way, with the independent variable, the thing we varied, which was the concentration, on the x-axis, and the dependent variable, the thing we measured, which was the time, on the y-axis. We can clearly see that as the concentration increases, the time to collect the same volume of gas is decreasing, so the rate is getting faster. We can't easily see whether our prediction is correct, though. To do this, we need to change our times into rates, so we can plot a graph to see how the concentration affects the rate of the reaction. If the time we measured was how many seconds it took to fill one measuring cylinder, then the rate is the number of measuring cylinders we could fill per second. We find that by working out 1 divided by the average time we measured. We can see that the rate increases as the concentration increases, and we can plot this as a graph. The points give a good straight line of best fit that would pass through the origin, showing that the rate of reaction is directly proportional to the concentration of the acid. We can also see that one of the points, for 2.4 moles per dm cubed, does not fit the line of best fit. This too is an anomaly, and a ring should be drawn around it, and it should not be included in the line of best fit. From our graph of rate versus concentration, we can see that when the concentration is doubled from 1 mole per dm cubed to 2 moles per dm cubed, the rate increases from 0.02 to 0.04 seconds to the minus 1, so the rate doubles when the concentration is doubled, which is what we predict. The effect of pressure for gases is the same as the effect of concentration for solutions. Greater pressure means more gas particles per centimetre cubed. We should know that the same volume of any gas contains the same number of gas particles, so it doesn't matter which gas we're dealing with. When we increase the pressure, we can do that by making the volume smaller, so the same number of particles are contained in fewer centimetres cubed of volume. Alternatively, we could put more gas particles into the same volume. Either way, the effect is the same, more gas particles per centimetre cubed, which means that collisions will occur more frequently, and so there will be more frequent successful collisions, and the rate will increase. The effect of temperature on the rate of a reaction is a little more complicated because there are two parts to collision theory and both affect the rate of reaction in this case. When we increase the temperature, the particles move faster, which means they have more kinetic energy. Because the particles are moving more quickly, they will collide more frequently. But also, when they collide, they will be colliding with more energy, so each collision that takes place is more likely to have energy greater than the activation energy. We will therefore have more frequent collisions, and each collision is more likely to be successful. So we can predict that as the temperature increases, the rate not only increases, but increases by larger amounts. We can use the disappearing cross experiment that we described earlier as one possible way to investigate the effect of temperature on rate. We do the experiment at a number of different temperatures and measure the time it takes in each experiment for the cross to become obscured by the precipitate. Here are the results from such an experiment. The times shown here are averages over several repeats, with anomalies not included. The graph for our results clearly shows that as the temperature increases, the time for the cross to disappear gets less. But we can't see from this graph how the temperature actually affects the rate. As before, we'd need to turn the times into rates. We do this by calculating rate equals 1 divided by time, and when we do this, we can see that the rate increases with temperature, but it is not until we plot this as a graph that we can see that the line of best fit is not straight. Our prediction is correct. The graph curves upwards as the temperature increases, showing that the rate is increasing by progressively larger amounts as the temperature increases. The effect of surface area on rate of reaction has already been discussed. Collisions can only happen on the surface of a solid, so if we want to increase the rate of reaction, we need to have more surface for collisions to happen on. If we have the same amount of our solid reactant, we can increase its surface area by breaking it into smaller pieces. Large lumps will have a low surface area, and hence relatively few successful collisions can take place per second. If we crush the lumps into smaller pieces, we expose more surface, and so successful collisions will be more frequent. If we really want to increase the rate of reaction, we need to powder our solid to maximise its surface area. We can also increase the rate of a reaction by using a catalyst. A catalyst is a substance which increases the rate of a reaction without itself being used up. Manganese 4 oxide, often called manganese dioxide, is a good example of a catalyst that speeds up the decomposition of hydrogen peroxide into oxygen gas and water. Here's the equation for the reaction. Once the catalyst is added, the hydrogen peroxide solution fizzes and oxygen is produced. When the reaction is finished and the fizzing stops, all the manganese 4 oxide is still there in the flask. In fact, we could filter it off and use it again and again. Notice also that the manganese 4 oxide isn't written as part of the balanced equation because it's not a reactant or a product. We could write it over the arrow, showing it as one of the conditions under which the reaction took place if we wanted. We can use collision theory to explain how catalysts increase the rate of a reaction too. Remember that for a reaction, the reactants must collide, and they must collide with energy greater than the activation energy for the collision to be successful. What a catalyst does is provide a place where the activation energy for the reaction is lower. This means that the catalyst gives each collision a much greater chance of being successful, so more successful collisions per second and a higher rate of reaction. Not surprisingly, for a solid catalyst, the higher the surface area, the more effective it is in increasing the rate of the reaction, so catalysts are often given rough, irregular surfaces, or powdered. To be really clear whether a substance is a reactant or a catalyst, we need to determine whether it is used up in the reaction. We can do this by looking at the balanced equation and seeing whether the substance is shown as a reactant on the left side of the arrow. If it's shown here, it's not a catalyst, and it will be used up when the reaction takes place. We can also observe the reaction. If the substance is still present in the same quantity, unchanged, when the reaction is finished, it's a catalyst. One example of a catalyst is the combination of platinum, rhodium and palladium metals used in a car's exhaust system. The hot gases from the engine contain carbon monoxide, which is toxic, nitrogen oxides which cause acid rain, and unburnt hydrocarbons which can lead to smog and cause health problems. The catalyst system causes these gases to react. The nitrogen oxides are turned into harmless nitrogen. The carbon monoxide is turned into carbon dioxide, which is not toxic, and the unburnt hydrocarbons are burnt to produce carbon dioxide and water. Another important example of a catalyst used to increase the rate of a reaction is in the Haber process, used for the industrial production of ammonia. The catalyst used here is iron. Using the catalyst allows the reactor to work at a lower temperature and still achieve the same rate of reaction, so less fuel is burnt. Using less fuel conserves finite fossil fuel resources, and minimises greenhouse gas emissions, so we can see that understanding how to control the rate of reactions is of great significance for our environment and for a sustainable future.